Why did the point at the center of the circle refuse to date any of the points on the edge of the circle? She didn't want to have an equidistant relationship. And with that, we're going to go ahead and look at rotations. So one thing I'd like you to do is list some objects that you've seen rotate or have rotating parts. I'm showing a few here, including clocks, washing machines, CD drives. And what shape do you notice that is common among these rotating objects, and why? Well, you'll probably notice that they are all circles. And why is that? Well, all the points are equidistant from the point of rotation, or the center of the circle. So again, what is a rotation? If I can go ahead and adjust this, and you can see I'm rotating this point. And for our purposes, we're normally going to rotate clockwise. And basically, how are these points traveling around the point of rotation? So I'm rotating about, let's see, it should be point F. Yeah. So wherever point F is, then if I show you my circles here, you can see that F is the center of rotation. And as I rotate my object around, it's traveling on a circular path, which kind of makes sense from what we know of points of rotation. There are two directions for rotation, clockwise and counterclockwise. You can mimic counterclockwise by curling the fingers in your right hand. And some of you may have a set of notes where I actually have this switched to make sure that the counterclockwise direction is the right hand, okay? And then the way I do the hand is the way your fingers curl around your thumb. That is counterclockwise if you're looking at your thumb. Clockwise, which you can say, well, look at a clock, but you can also mimic it with your left hand. So your left hand actually curls in the opposite direction. For our purposes, we will assume that rotations are clockwise unless stated otherwise. So because the path traveled is a circle, then the preimage and the image point are equidistant from the center of rotation. So you can actually tell if a point was rotated about another if both points are the same distance from the point of rotation. So in this example, we're going to determine which point, C, D, or E, could have been point B after rotation about point A. Well, the distance from A to B is pretty easy to measure. It's just 5. And then let me go ahead and measure the distance from A to C. And I make a right triangle, and I'm going to use the Pythagorean theorem. I could use a distance relationship. Pythagorean theorem takes less space. So I have AC squared equals 4 squared plus 1 squared, or 16 plus 1, 17. So this length is the square root of 17. So it's less than 5, but more than 4. Then I can look at the next distance from A to D, and I'm going to make a right triangle for that one. And you can see that AD squared is going to be 5 squared plus 1 squared, or 25 plus 1, which is 26. So the length is the square root of 26, which means it's a little bigger than 5. Finally, I'm going to go ahead and look at the distance for AE squared, which is this one. So I have a side of length 4 and a side of length 3. Do Pythagorean theorem, and I get 25. And when I take the square root of that, I get 5. So the point that did result as a rotation about point A is point E. C and D are not the same distance, so they could not have been the rotation of B about point A. So for further reflection, why are spinning parts normally circular? And think of equidistant relationships. That's how spinning behaves. And what is the difference between clockwise and counterclockwise?